we can discuss the concept of frequency shift keying. It is one of the digital modulated technique in which the frequency of the sinusoidal carrier is switched between the two amplitude levels 0 and 1 of the input digital signal. We know that for a digital modulated system, the input is a digital signal, and based on the input digital signal having only two levels, the frequency of the sinusoidal carrier is switched between the two amplitude levels of the input signal by keeping the amplitude and phase of the carrier as constant. In this figure, you can observe that our input data is a digital signal, which is in the form of 10101, and this is our synchronous carrier. And here in the in the FSK modulated signal, you can see that for data bit 1, there is a change in the frequency of the carrier to some higher frequency FH. A high frequency signal can be distinguished with a low frequency signal that in such a way that there is a compression over time. So the signal gets compressed over time. Then you can say that it is high frequency signal because we know the inverse proportionality between the frequency and the time. Similarly, for 0-bit data, you can see that the frequency of carrier changes to some low frequency FL, whereby you can see some the signal expansion over time. So like that, based on the input signal magnitude, the frequency of the carrier will change, but the amplitude as well as the phase, that is in the direction, doesn't change. And this FSK signal is also known as two-array FSK or binary FSK, in which you will have two phase changes, two frequency changes. One frequency change is 2 pi, you can see that 2 pi FC, you can see the change in the frequency. Actual frequency is 2 pi FC, and you can observe plus omega change. That is, there is an increase in the carrier frequency to some capital omega multiplied by t when the data bit is 1. Similarly, FSK signal is defined as AC cos 2 pi FC minus omega. There is a decrease in the frequency when the input data bit is 0. So like that, you can define FSK signal. And here again, we have written the same expression, AC cos 2 pi FC plus omega into t when the data bit is 1. And similarly, AC cos 2 pi FC minus omega into t for data bit 0. Now let us take 2 pi as common here. If you take, because 2 pi FC is an angular frequency, let us split into the natural frequency. So AC cos, take 2 pi as common. If you take 2 pi as common from this, you will get FC plus omega by 2 pi whole multiplied by t. This is when the data bit is 1. And you will get 2 pi into FC minus omega by 2 pi multiplied by t when data bit is 0. So you can say that high frequency is FC plus omega by 2 pi and low frequency FL as FC minus omega by 2 pi with the synchronous carrier or sinusoidal carrier as AC cos omega CT. And here you can observe that the power dissipated per symbol PS is equal to AC square by AC by root 2 whole square divided by R. So just we are going to replace AC as root 2 PS to write it as a 1-bit energy carrier. We already discussed this concept in ASK as well as PSK modulated techniques. Let us replace AC as root 2 PS. That we can see in the next slide. So here what we are doing, we are going to replace AC as root 2 PS, and also we have replaced FC plus omega by 2 pi as FH and FC minus omega by 2 pi as some FL. So this is the FSK expression. Let us replace it as AC as root 2 PS. And again, we are going to write it into 1-bit energy carriers. In ASK and PSK, we have only one frequency change. That's why directly we have taken it as phi1 of t. Only one and 1-bit energy carrier. But here, because we have two carrier frequencies, so one is increase in the carrier frequency to FH when data bit is 1 and decrease in the carrier frequency when the data bit is 0. So that's why you have two 1-bit energy carriers, that is phi 1 of t and phi 2 of t. That's why let us write this expression as root 2. Let us multiply the numerator and denominator with root ts by ts. So multiply and divide by root ts. If you do like this, then you can write it in the form of symbol energy. This is symbol energy, ES, which is the product of PS and TS into this 2 gets, you can move the 2 here. So root over 2 by TS cos 2 by FHT. So this is 1-bit energy carrier of the higher frequency. Let us suppose define it as some phi 1 of T. And similarly, you can get for data bit 0 as the low for the low frequency, let that 1-bit energy carrier be phi 2 of t. So phi 2 of t is root 2 by ts cos 2 by FLT. This is when the input is 0. Now you can see the general expression of FSK signal as root ps into ts into 1-bit energy carrier phi 1 of t due to high frequency FH. And this is when data bit is 1. When data bit is 0, it is root ps into ts into uh, the 1-bit energy carrier, which is phi 2 of t. So let us go through the generation technique. So coming to the generation of BFSK, here we already seen the general expression for FSK signal. So it consists of phi 1 of t, that is 1-bit energy carrier due to high frequency, and 1-bit energy carrier due to low frequency. That's why in order to get FSK signal, overall FSK signal, it should be the combination of data bit 1 and 0. When, for example, if the upcoming data bit is 1, that is of higher magnitude, then here you can see the inputs to the upper modulator. This whole section is the upper modulator, and this is lower modulator. In this upper modulator, you can see that the input is applied to the input is BH of t, and for the lower modulator, input is BL of t, where BH of t is directly equal to B of t, and BL of t is a complement of B of t, because BL of t is applied to the inverter. For example, upcoming data bit is 1, then BH of t is directly equal to B of t. Then this BH of t is multiplied with the root PS into TS. At that time, BL of t will be 0. That is, no input is applied to the lower modulator. So input is applied only to the upper modulator. So you will get output only from the upper modulator, not from the lower modulator. So BH of t is multiplied by root PSTS, and it is multiplied by 1-bit energy carrier due to higher frequency. So you will get SH of t, which is equal to BH of t multiplied by root PSTS multiplied by phi 1 of t. At the time, the output, no output is from SL of t. Next, for example, if you apply the data bit as 0, then BH of t is 0, and there is no output from SH of t at that instant. And BL of t will be 1, then that is multiplied with root PSTS, and because here you are using the level shifter, this will raise the magnitude by root PS into TS, and that is multiplied by phi 2 of t to produce the output of lower modulator, which is SL of t. And overall FSK signal is a combination of SH of t and SL of t. It is SH of t plus SL of t. So here you can see the working principle. When B of t is 1, we already discussed that B of t is directly equal to BH of t. So directly when B of t is 1, BH of t will also be 1, and when B of t is 0, BH of t is also 0. But BL of t is a complement of, B of t. So that's why when B of t is 1, BL of t will be 0, like that you will get. And whenever the data bit is 1, upcoming data bit is 1, output is due to the upper modulator, otherwise the output is from the lower modulator. If the data bit is 0, output is from lower modulator. The sum of these two outputs is the overall FSK signal. These equations are the same expressions that we have observed from the block diagram. SH of t is BH of t into root PSTS into this whole thing is phi1 of t. Similarly, SL of t is BL of t into root PSTS multiplied by phi2 of t. So overall, BFSK signal is the sum of SH of t and SL of t. Just we have added the two expressions, and we know that this whole thing is phi1 of t. So we have written it as phi1 of t, and this whole factor we have written it as phi2 of t. And here you can see that this is symbol energy. This you can write it as a symbol energy. So therefore, BH of t overall FSK signal is BH of t into root ES into phi1 of t plus BL of t into root ES into phi2 of t. And here you can see the calculation of Euclidean distance of BFSK for two orthogonal carriers. We have seen the magnitudes of 1-bit energy carriers for FH, let it be phi1 of t, and phi2 of t let be for FL. And let us see the minimum amount of distance for two orthogonal carriers. Uh, Here the magnitude is root ES for phi2 of t as well as same magnitude is for phi1 of t, because in the last slide we have seen the expression. So from the Pythagoras theorem you can get the overall distance as root over root ES square plus root ES square, that is root over 2 ES. So root over 2 into PSTS is our Euclidean distance. But the Euclidean distance of ASK is root ES and Euclidean distance of PSK is 2 root ES. So if you compare, we know that the lower the value of the lower the value of the lower the value of Euclidean distance, better will be the probability of error. So because the Euclidean distance of FSK is greater than ASK and less than PSK, its probability of error lies in between ASK and PSK. That is the conclusion from this slide. This is the bandwidth evaluation, the same thing that we discussed for ASK as well as FSK, but here we have two frequencies, FH and FL. So now you are going to calculate the distance between FH and FL. So we know that the message is distributed from FH minus FB to FH plus FB. Similarly, for FL also, the message is distributed from FL minus FB to FL plus FB. So if you take the different distance between these two, that is FP plus FP. For example, if you take FH minus FL as 2FP, the minimum bandwidth required for transmitting the FSK signal is 4FP. So this is the main drawback of BFSK. So it needs large amount of bandwidth for signal transmission. That is a drawback of FSK. So here we have two types of detection techniques. One is coherent detection and other is non-coherent detection. In the coherent detection, you can see that we know that for coherent detection, we have synchronous carrier or coherent carrier. But here we have in FSK, we know that there are two carriers. One is for low frequency and other is the higher frequency. And similar to the transmitter, here also we have two correlators. One is upper correlator and other is lower correlator. So incoming BFSK signal is multiplied with cos 2 pi FHT in the upper correlator and allowed to the low pass filter. And we are considering the output of upper correlator as L1. Similarly, it is also multiplied with the lower correlator with cos 2 pi FLT and applied to the low pass filter. Let the output from the lower correlator be L2. Here, because we have two outputs, let us apply to the comparator instead of decision device. So if L1 is greater than L2, you can take the output as 1, else the output is considered as 0. For example, you can see the output of upper correlator. Upper correlator, we have seen that it is multiplied by cos 2 pi FHT. What? BFSK signal. So let us take the BFSK signal in this form, that is root over 2 PS into BH of t into cos 2 pi FHT plus root 2 PS into BL of t into cos 2 pi FLT. Let us multiply it with cos 2 pi FHT. Then let us see. Then it will be cos square 2 pi FHT first term, and second term is cos 2 pi FHT into cos 2 pi FLT. So cos square you can write it as 1 plus cos 2x by 2. In this you can see that this is a higher frequency. Our low pass filter does not allow the high frequencies as well as the mixed frequencies. That's why the low pass filter output will be only root overall root 2ps whole divided by 2. So it gets cancelled. So you will get root over ps by 2 into bh of t. And similarly, the output of the low pass filter 2 is root ps by 2 into pl of t. Now we will compare L1 with L2. If L1 is greater than L2, output is 1. Else the output is 0. This is a non-coherent detection of BFSK. In this, the incoming BFSK signal is here we doesn't you make use of correlator, that is coherent carrier or synchronous carrier. So this is called as asynchronous detection. So incoming BFSK signal first is it also consists of two detectors. One is upper non-coherent detector and the lower non-coherent detector. In the upper non-coherent detector, we have bandpass filter followed by envelope detector and sampler. So this bandpass filter, upper bandpass filter has cutoff of only FH. So the output of upper non-coherent detector is due to FH. Let us suppose assume it as L1. And the output of lower non-coherent detector is L2, that is due to the bandpass filter FL. And the bandpass filter output is applied to the rectifier. So rectifier converts it into a DC component, pulsating DC, and which is smoothened by the low pass filter. And the low pass filter output is sampled at each and every instant and to extract the respective outputs as L1. Similarly, the same is processed in the lower non-coherent detector, but the frequency is due to FL. Okay. Here you can see that the rectifier converts the incoming signal into pulsating DC, which is smoothened by the low pass filter, and sampler generates the DC component at distinct intervals. So as a whole, the output of upper correlator is due to FH only, because the the upper band pass filter allows only FH component, and the lower detector allows only FL component. So the output due to the output due to upper detector is due to FH only. Now comparator takes the difference between L1 and L2. If L1 greater than L2, output is considered detected as 1. Otherwise, the demodulated output is 0. Here you can see the advantages. Here FSK has no amplitude variations similar to PSK, so it is less susceptible to noise. And similarly, the Euclidean distance is more than ASK, but less than, sorry, it's less than PSK. Sorry. Because the Euclidean distance is more than ASK, its probability of error is less when compared to ASK. But when compared to PSK, the probability of error is more. The generation of BFSK is easy, and also the bandwidth required for BFSK is very high. This is the main drawback of BFSK. And also the error rate is higher than BPSK but less than BASK. So that's why FSK is used in paging services, cordless telephony, where nearby transmissions, uh, like paging services, cordless telephony. Similarly, caller ID applications, in the earlier days, it is used to do for telephone transmission via telephone wires, optical fiber, or wireless media. But it's for because it needs large amount of bandwidth, so it's preferred for low bandwidth systems. Thank you one and all for listening. In the next module, we can discuss the concept of quadrature phase shift keying.